This video is all about the central limit theorem. The central limit theorem is the most important theorem of all of statistics. So what we're going to be talking about in this video on the central limit theorem will be sampling distributions. So that's going to be the distribution of all possible samples that you can take for a particular mean or a proportion or some other statistic where you're looking at all samples of the same sample size. Then we'll look at the central limit theorem, the most important theorem of all of statistics, and we'll start out with the central limit theorem for means, which is a major one. And then we'll talk about what if you wanted to look at sums instead of means. And there is a central limit theorem for sums. And then we'll say, well, what if you have a yes-no question and we want to find out what the distribution is for all the possible samples that can be taken from a yes-no question. And that'll be the central limit theorem for proportions. So let's start out by talking about sampling distributions. So a sampling distribution means the following. Given a population and sample size n, the sampling distribution of a statistic, remember a statistic could be the mean, could be the standard deviation, it could be the median, there are many, many statistics, is the distribution of all values of the statistic for all possible samples of size n. So if you conduct a study and you look at your data, then you're going to get your statistic. And then tomorrow, let's suppose you conduct a study with the same sample size. Well, you'll get another statistic. It might still be the mean or the median, but it might be a different number. Well, you could do this over and over and over again, and you could draw a histogram of all the possible values that you get, for example. And the distribution, which the histogram will portray that shape of the distribution, is what we're going to be talking about, and that is a sampling distribution. So let's start out by talking about a sampling distribution of the mean. So it's pretty much the same definition, but we're going to throw in the word mean instead of statistic. So we're given a population and sample size n. The sampling distribution of the mean is the distribution of all the means for all possible samples of size n. So think about conducting a study. You might be surveying people about, I don't know, how much do you weigh? And let's say that the population is all people on Earth. Well, you could survey, say, 500 people, and you have many, 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 many choices of which 500 people that you could survey. But no matter which choice you take of 500 people, there is going to be a mean weight. If you look at all the mean weights for all the possible choices for those 500 people, and you draw a histogram, then that histogram will portray the shape of that distribution, and that is called the sampling distribution of the mean. Notice the sampling distribution, the sampling distribution, is different from the distribution of a particular sample. The sampling distribution is about all possible samples, not about a particular sample. So since we're talking about a distribution of all possible means, think about a mean being a number, and we're going to have many, many, many numbers. And you're used to when you have a bunch of numbers, you can take the mean of those numbers. So the mean of all the possible sample means, we use a notation mu sub x bar, because mu means the population mean, and then of x bar, or of all possible sample means. Similarly, if we look at all possible sample means as a list of means, those are numbers, so we get a big long list of numbers, we can calculate that list's standard deviation. And we say the standard deviation of the sample means is represented by sigma sub x bar. Sigma means a population standard deviation of all possible, and x bar, so of all possible sample means. So that's the standard deviation of the sample means. So now let's look at a fun little example. Let's suppose you had 4 people, okay? So you got 4 cute little kids, and one is 2 feet tall, another is 3 feet tall, a third person is 4 feet tall, and then the fourth is 5 feet tall. And we want to look at the sampling distribution with sample size 2. So in particular, I could take the sample of the first and the second. That'd be the 2-foot and the 3-foot child. And if I take the sample mean of 2 and 3, I get 2.5. But I could also do the first one, the first child, and the third child. That would be a different sample of size 2. And the sample mean of 2 and 4 is 3. I could do more. I could take the sample mean of the first child and the fourth child, and that would be the mean of 2 and 5, which is 3.5. 5 plus 2 is 7. 7 halves is 3.5. Well, I'm not done yet. I could also look at the second child and the third child, and that means I take the mean of 3 and 4, and the average or the mean of 3 and 4 is 3.5. I could do more. I could take the second child and the fourth child, and they will have a mean height of 4. And then finally, I could take the third child and the fourth child, and the mean of 4 and 5 is 4.5. These are all the possible samples that I could get by taking 2 different children. Now I could take the data, looking at all the possible x bars, 2.5, 3, 3.5, 3.5, 4, and 4.5. Now that we have all of the sample means, let's talk about just the population mean. Well, if I take the average of 2, 3, 4, and 5, well, 2 plus 3 is 5, plus 4 is 9, plus 5 more is 14. 14 divided by 4 is 3.5. So I can say the population mean is 3.5 for these 4 children. I could also take the standard deviation of 2, 3, 4, and 5, and I popped that in my calculator, and what I got was that sigma, the population mean, is about equal to 1.12. So that is the population mean and the population standard deviation. Now we want to talk about the sampling distributions statistics. So I can look at the mean of 2.5, 3, 3.5, 3.5, 4, and 4.5. And when I add those up and divide by 6, I, not coincidentally, got 3.5. So I say that mu sub x bar, which is the population of all possible sample means, is 3.5. I can also take the standard deviation of these 6 numbers. And the standard deviation, which is sigma sub x bar, because the standard deviation of the x bars, turns out to be 0.79. Notice the standard deviation of all the possible sample means is not the same thing as the standard deviation of the data that we started with. So sigma sub x bar is 0.79, but sigma is 1.12. So next, let's take a look at a simulation that I developed about the central limit theorem. Maybe we can see what's going on here. Okay, so here is the program that I wrote. It's to discover the central limit theorem activity. And what we can do is we can first choose what kind of distribution do we want to have it start with. So I'm going to start with, how about a uniform distribution. So hopefully you know a uniform distribution is flat, looks like a rectangle, and just the mean is 200, the standard deviation happens to be 115.47 for this particular example. Now, what about the sampling distribution? So if I choose n equals 2, then there's my sampling distribution. So what that does is it randomly grabs a whole bunch of values from the uniform distribution, and the computer calculates the mean of all those values and the standard deviation of all those values. And notice it doesn't look uniform anymore. Notice a mean is still about the same, 199.84, which is about 200. The standard deviation is smaller. So we started with 115, we ended up with 81.75. How about a bigger one? How about n equals 100? Okay, now things have changed a lot. First thing is the mean of the sampling distribution, mu sub x bar, is still around 200. That really hasn't changed. On the other hand, standard deviation changed a lot. Notice it went from about 115 to about 11.5 or 6 or so. It actually dropped by a factor of 10. So the standard deviation of the population compared to the standard deviation of the sampling distribution is not the same. And in fact, 10 just happens to be the square root of 100. See if that works. How about n equals 25? So if n equals 25, then notice that the mean stays about the same. But now if we take sigma versus sigma sub x bar, it's been dropped a bunch. And in fact, if you multiply by 23 by 5, you get about 115. And the square root of 25 is 5. So we see that the sampling distribution seems to have the same mean, but the standard deviation gets decreased by a factor of the square root of the sample size. Okay, this works, it turns out, for any possible distribution you might want to look at. That same idea happens. In fact, let's play around. I can even, how about a user distribution? I get to draw my own. So how about a multimodal distribution? And what happens if we look at n equals 100? Okay, notice that we're still dividing by about 10 for the standard deviation. The mean is pretty similar, the same. Notice that we started with this multimodal distribution all over the place. Kind of looks like a cool landscape. We end up with something that looks pretty normal. And in fact, if we go to scale, then that's what it looked like. Because again, we have this big peak in the middle for the sampling distribution, whereas it's just a bunch of little bumps all over. And it turns out that it is somewhat normal. So let's take a look at the central limit theorem that will help us understand and actually show us what's going on in terms of the theorem. All right, the central limit theorem states the following. Let x bar denote the mean of a random sample of sample size n from a population having mean mu and standard deviation sigma. Then we have the following. Mu sub x bar is equal to mu. So if we look at all possible samples of sample size n, and we look at their means, then the mean of the means is equal to the mean of the population. And sigma sub x bar is equal to sigma over the square root of n. So that tells us the standard deviation of all possible sample means is equal to the population standard deviation divided by the square root of the sample size. And something very, very important to note is that if n gets large, sigma sub x bar gets very, very small. So that means if you have a very, very small sigma sub x bar, and you happen to randomly grab one sample of that size, then it's very likely that the sample mean from that sample will be close to the population mean. Because if the standard deviation is small, you're very likely to be close to the population mean, which is mu sub x bar, which happens to be mu. So then there's part two. And part two says, when the distribution of the population is normal, so is the distribution of x bar for any n. That's not too surprising, not that useful either, because usually you don't have a normal distribution to start with, because you're just doing some survey. But on the other hand, the second part says that if you have a large sample size, the distribution of x bar is approximately normal, regardless of the population distribution. Now, we saw that in the visualization that we just saw, where we started with a uniform distribution and it was pretty bell-shaped, or we started with that funky distribution and we still got a pretty bell-shaped distribution for the sampling distribution. So what does large mean? Kind of the rule of thumb, what a lot of people go by, and basically it usually gives you about a decimal place of accuracy, is that if n is greater than 30, so in other words, 31 or bigger, then we're going to call n large. So this is the central limit theorem. Again, the most important theorem of all of statistics, undeniably. So now let's look at this again. We can look at this sampling distribution and realize that our mu was 3.5, mu sub x bar was also 3.5. That works, that's a good thing. And when the mean of all the statistics that you could take is equal to the population parameter, we're going to call that an unbiased estimator. So in this case, mu and mu sub x bar were equal, so that means x bar is an unbiased estimator for the population mean. So if you take a sample, then you look at the mean of that sample, that's your best guess for the mean of the population. On the other hand, if we look at the range, you look at the range of this group of people, the range is 3. 5 minus 2 is 3. On the other hand, if you look at the sample ranges, then we get 2 to 3, that has a range of 1. 2 to 4 has a range of 2. 2 to 5 has a range of 3. 3 to 4 has a range of 1. 3 to 5 has a range of 2. And 4 to 5 has a range of 1. So if instead of the means that we're looking at, look at the ranges for the sample. Okay, now here's the bad news. If we take the mean of all these ranges, so you go 1 plus 2 plus 3 plus 1 plus 2 plus 1, divide by 6, you get 1.67. And that is certainly not equal to the range of the population. And that will always be true. The range, or just about always true, the range for the population and the mean of all possible ranges for samples of size n will not be the same. The range for the population will pretty much always be bigger than the mean of the ranges of a fixed sample size. So that means that the range is a biased estimator. So the sample range is a biased estimator. So if you're conducting a study and you do the sample and you look at the range of your sample, do not use that to decide what is the most likely number for the range of the population, because you're going to be off. Instead, you got to do really advanced statistics. We're not going there. But in this class, we're going to be looking at unbiased estimators, or at least somewhat unbiased estimators, mostly unbiased. So let's take a look. An unbiased estimator, by definition, is a statistic whose sampling distribution has a mean that is equal to the population parameter. The sample mean is an unbiased estimator for the population mean. That comes right from the central limit theorem that we just had, because mu sub x bar equals mu. Turns out the sample proportion is also an unbiased estimator for the population proportion. So if you take a study with a yes-no question, and you look at the proportion of yeses for your study, and that is actually your best guess for the proportion of yes answers for the entire population. Turns out the sample variance is also an unbiased estimator for the population variance. But the sample range is biased. It is a biased estimator for the population range. So there's some examples. We're going to mostly look at the mean and the proportion in this class. Those are the main ones. So now let's look at an example. So now we're going to apply the central limit theorem for this example. So it says, suppose the average amount of time that it takes for college students to complete their degree is 4.7 years. The standard deviation is 0.3. What is the probability that 40 randomly selected college students will have an average completion time of less than 4.6 years? So to do this, we're going to use the central limit theorem. So here's a summary of what we have. The mean time to complete the degree is 4.7. The standard deviation is 0.3. The sample size is 40. And we want the probability that a sample mean is less than 4.6. So in particular, the central limit theorem says that x bar is normally distributed. So the n means normally distributed with mean equal the population mean, which is 4.7, and standard deviation equal the population standard deviation, which is 0.3, divided by the square root of n, and n is 40. So it helps to pop that in a calculator, write that as a decimal. We can say that is normally distributed with mean 4.7 and standard deviation 0.0474 is what I got when I took 0.3 divided by root 40. So let's look at a picture of all of this. So what we're looking at now is we're told that we have a normal distribution because the central limit theorem says that the sample size is 40, which is greater than 30. So we can say that the distribution is approximately normal. So I can draw my normal curve. The mean is 4.7 for the sampling distribution. And we want to find the probability that x bar is less than 4.6. So I shade in everything to the left of 4.6. And I want that area. So to get that area, what I need to do now is go to my calculator. So here's the calculator. I'm going to scroll down a bit. And I have a normal distribution. So I'm going to click on normal probability. And then the low, well, it's as far left as you can get. So the low is negative 9999999. The high was 4.6. The mean was 4.7. And the standard deviation was 0.0474. And I hit calculate. And there's my probability, about 0.01744, etc. So now I can go back to the question and understand it. So I can now say that the probability that a random sample of 40 students having their average time to complete the degree being less than 4.6 is equal to 0.0174 about. And that's the answer to that question. Now let's do another example. And this one is money. It's a good way to make a lot of money or understand how to make money and how to invest. So here's an example. Suppose that stock increases are normally distributed with a mean of 3% and a standard deviation of 5%. If your randomly selected portfolio consists of 20 stocks, what is the probability that your portfolio will lose money? Now, one assumption that we need to make for this, which is probably not completely true, but it's an assumption, and that is that these stocks are independent of each other. So if one goes up, we have no idea what the other is going to do. So that may not be true in the stock market. If you have a very diversified portfolio, you got much better independence. And that's one of the reasons why you want a diversified portfolio for investments. So let's look at all of this data or this paragraph and write down what these numbers are. So in particular, the mean stock increase was 3, mu equals 3, standard deviation was 5. Our sample size is 20, and we want the probability that X bar is less than 0, because losing money means you end up with a negative return or less than 0 return. So we can use the central limit theorem that says that X bar is normally distributed, because we're assuming that the original stocks were normally distributed, and that was kind of part 1 of the central limit theorem. If you don't want to have to assume it, then you better have a bigger portfolio of more stocks. And the mean of all possible samples of size 20 is equal to the population mean, or 3. And the standard deviation is equal to sigma over root n, or 5 over root 20. And I wrote that as a decimal, and I could say that's normally distributed with mean 3 and standard deviation 1.118. So again, I can look at a picture and say that here we have the mean is 3. We want to find out the probability that we end up with less than 0. So we shade in to the left of 0. And what is that probability? So guess what? We go to our calculator again. So here's the calculator, and again, I'm in the normal probability calculator. Again, my low is going to be negative 99999. The high this time will be 0, because losing money means that you didn't make more than $0. The mean was 3, and the standard deviation was 1.118. And we want the probability, I leave that blank, and I hit calculate. Notice it's a very small probability. It's 0.003644 about. So that's one of the main reasons why you want a diversified portfolio with many different stocks instead of putting all your eggs in one basket. Because if you're worried about losing money, you have a very small chance of losing money if you invest for a long period of time in many different stocks. So let's go back to the question. And we could say that the probability that X bar is less than 0 is equal to 0.0036, or there is about 0.36% chance of losing money. Very small percent chance, 0.36. So now let's look at another example. Suppose the average GPA of college students is 3.1 and the standard deviation is 0.7. A class of 35 randomly selected students will be considered high risk if their mean GPA is in the bottom 2nd percentile. What is the largest mean GPA that will be considered high risk? So in this case, what we want to do is we want to write down all these numbers and turn them into symbols. So in particular, our mean GPA was 3.1. The standard deviation was 0.7, so sigma is 0.7. Our sample size was 35. And we're asked to find the 2nd percentile. So in particular, we can say that the probability that x is less than that percentile is equal to 0.02, so 2%. We can use the central limit theorem, and that says that x bar is normally distributed with mean mu, or 3.1, standard deviation sigma over the square root of n, or 0.7 over root 35. I wrote that as decimal, and I could say that is normally distributed with mean 3.1 and standard deviation 0.1183 when I put that in my calculator. Again, we could draw a picture. This time we're given the probability. So we know the area to the left of this unknown number is 0.02. We want to find out what this unknown number is. So now we can use the calculator. So here's the calculator again. We want to find out the unknown number is the high, and we want to know less than that. So the lowest is still negative a bunch of nines. The high now is unknown, so that is empty. That's what we want. The mean this time is 3.1, and the standard deviation is 0.1183. The probability was given as 0.02. And I hit calculate, and there we have it, about 2.86 or so. So let's go back to the question and see what we've got. So what we found out is that the probability that x bar is less than 2.8570 is equal to 0.02, or in other words, the second percentile is equal to 2.8570 or so. And there's our answer. So let's look at the central limit theorem for sums. So sometimes you're more interested in finding sums than you are in finding the mean. And an example of that is if you're in business, you're much more interested in finding out the total amount of money you have at the end of the day than the average amount of money people spent, because it's all about how much money comes in. So here's the central limit theorem for sums. If the collection of all random samples of size n are taken from a population having mean mu and standard deviation sigma, then the sampling distribution of the sums will have mean n times mu and standard deviation the square root of n all times sigma. Note that n times mu, if you take the mean and multiply by your sample size, that gives you a total. The standard deviation, root n times sigma, that literally comes by taking sigma over root n, multiplying by n, doing a little algebra, and that's what you end up getting. And then the normality piece is the same as before. If the population is normally distributed, or if the sample size is large, larger than 30 in our case, then the distribution of the sums is also approximately normal. So that's a central limit theorem for sums. Let's apply it. So here we have the central limit theorem for sums example. The average family that goes to the carnival spends $65. The standard deviation is $15. If 80 randomly selected families are chosen, what is the probability that they will spend a total of more than $5,000? So notice that this is a central limit theorem for sums because of the word total. We're not looking at the average amount that they're spending. We want the total amount of money that comes in from those 80 families. And a total is a sum. So now let's take all these numbers and put them into symbols. So we're given the mean was 65, the standard deviation was 15, the sample size was 80, We want the probability that the total, or the summation of x, is greater than 5,000. So we can use the central limit theorem. So what that says is the summation of all x's, or those x's, has a normal distribution. Notice our sample size was 80, which is bigger than 30. So we don't need to make any assumptions about normality. We know that the sampling distribution is approximately normal. The mean is going to be mu times n, or 65 times 80. And the standard deviation will be sigma times root n, or 15 times root 80. And that I worked out is normally distributed. 65 times 80 is 5,200. And 15 times root 80 is around 134. We can draw a picture. We want to find out the probability that this sum is greater than 5,000. So I have a normal distribution. Its mean was 5,200. 5,000 is a bit to the left of that. And I shade in everything to the right, because greater than is to the right of 5,000. And I want to find out what is that area, or what is that probability. So let's go to our calculator. So here's the calculator again. It's the same idea. We're using the central limit theorem. This time, if you remember, the low was 5,000. The high is infinity, or a bunch of nines. The mean for this one was 5,200. The standard deviation was about 134. And we want the probability, so we leave that blank. And I hit calculate. And there we have it. The probability is 0.93222, etc. So let's go back to the question and answer it. So we can conclude that the probability that the total sales for those 80 people, the summation of x, it will be greater than $5,000, that probability is about equal to 0.9322, or about a 93% chance. Pretty high chance. Okay, so now let's look at the central limit theorem for proportions. So if we had that yes-no question, we're talking about proportions and not means anymore. So the first thing to note is that we're not looking at greater than 30 or normal distribution. We need to make sure the following. First, we must have a binomial distribution. We've talked about that before. That's a yes-no question. And they're independent of each other. There's no bias. That's binomial. Second, the distribution must be large enough, not over 30. That's not what we're talking about anymore. Now we're talking about n times p must be greater than 5, and n times q must be greater than 5, where q is equal to 1 minus p. And just note, n times p, if you take the sample size times the proportion of yes answers, that's the number of yes answers. So that means you need to expect to have more than 5 yes answers, and similarly, n times q is the number of no answers. So you must expect to have more than 5 no answers. And if this is the case, then the binomial distribution is approximately normal with mu sub p hat. P hat is the sample proportion, so the mean of all possible sample proportions is equal to the population proportion. And sigma sub p hat, which means the standard deviation of all possible sample proportions, is equal to the square root of p times q divided by n. So that's a major theorem when you're dealing with proportions and we have a large enough sample size. That means the expected yeses and nos are both greater than 5, then we can use this. So here's an example. 12% of the United States population is left-handed, okay? And I'm one of them, by the way, I'm a lefty. If 200 randomly selected Americans are surveyed, What is the probability that fewer than 20 of them are left-handed? So let's go ahead and take a look at this. So here's what we have. We were told that 12% of the population was a lefty. 12% is 0.12, so P is 0.12. 1 minus P, that's Q. 1 minus 0.12 is 0.88. Okay, N is 200. We want the probability that P hat, that's the sample proportion, less than 0.1, because 20 out of 200 is 10%, or 0.1. We want the probability that P hat is less than 0.1. And what is that probability? Note, by the way, that if I take 0.12 and multiply by 200, I get 24. And 24 is definitely bigger than 5. And 0.88 times 200 is much bigger than 5. No issues. So we can actually use the central limit theorem. And that tells us that P hat is approximately normally distributed with mean P, or mean 0.12, and standard deviation, the square root of PQ over N. P was 0.12, Q is 0.88, and N was 200. And I popped that in my calculator, and I found that that square root was about equal to 0.023. We could draw a picture of this. Here's our 0.12, the center of this normal distribution. We want the probability that we're less than 0.1, so we fill in everything to the left of 0.1, and we find that out. Now I could use my calculator and come up with that area or that probability. So here's the calculator. I want the probability that we're less than 0.1. So the low is negative 9999999, whatever. Very small, less than means negative infinity. The high is 0.1. The mean, that was 0.12. And the standard deviation, 0.023. I want the probability, so I leave that blank. And I hit calculate. And there we have it. You get about 0.192269, etc. So now I can go and answer the question. So I can say that the probability that P hat is less than 0.1, or that out of those 200 in the sample, we get fewer than 20 lefties, is about equal to 0.1923. So not too small a probability. All right, let's look at another example. According to a recent Gallup poll, 18% of Americans are underemployed. If 150 Americans are randomly selected, find the probability that between 24 and 30 of them are underemployed. So notice there's a yes or no question. So we're in that central limit theorem for proportions idea. So let's pop in our numbers. 18% are underemployed, so P equals 0.18. Q is 1 minus P. 1 minus 0.18 is 0.82. We had a sample of 150 people. And we want to find out the probability that P hat is between 15% and 20%, or 0.15 and 0.2. So we use the central limit theorem. And notice we can do that because if we take 18% of 150, that's certainly bigger than 5, and 82% of 150 is also bigger than 5. So P hat is approximately normally distributed with mean P, or 0.18, and standard deviation square root of 0.18 times 0.82 divided by 150, or the square root of PQ over N. I pop that in my calculator, and that's normally distributed, mean 0.18, and standard deviation about 0.0314. Again, we can always look at the picture, and here's the mean of 0.18. We want to see in between 0.15, and 0.2. So that's this area over here, this between area. And I could go right to my calculator. So let's do that. So the low is 0.15. The high is 0.2. The mean was equal to 0.18. And the standard deviation was 0.0314. I want the probability, so I leave that blank. And I hit calculate. It's about 0.5682 or so. Now I can go answer the question. I can say that the probability that between 15% and 20% of a sample of size 150 is underemployed, that probability is about 0.5682. Let's go to the very last problem that I've got. And this is testing a claim. And we're going to be spending a lot of time on this coming up in the last half of the class. So here's a question. Is it likely that no more than 50% of voters support legalization of marijuana? A recent field poll of 1,636 Americans found that 1,096 of them support legalization of marijuana. So what is that probability that if you were to sample 1,636 randomly selected Americans, such that really 50% support legalization of marijuana, that you're going to have at least 1,096 of them say they support? This is a really important kind of question in which we're finding what's called a p-value. And that's going to come up in a little bit later in this class, not today. Just a note, by the way, I am recording this now, and who knows, by the time you're watching this, this could be years later. Maybe it's already been legalized and this is an irrelevant topic, but at least we can still understand the statistics, and we'll find out. Okay, and one more note. It turns out that if I take 1,096 and divide by 1,636, I get 0.67 or 67%. So that's what the sample had, 67%. That's bigger than 50%, but it's just a sample. So how likely would it be that if 50% of the voters supported legalization of marijuana, that we would end up with a sample so that 67% of the sample supported legalization of marijuana? How unusual is this survey under the assumption that 50% of voters support legalization of marijuana? So now let us test this claim. All right, so here's everything we've got. We're saying, well, the claim was that really it's only 50%. So that's P is 0.5, Q is 1 minus 0.5, or also 0.5. Our sample size was 1,636. We want the probability that P hat is greater than 0.67, because that was the proportion of the sample who supported legalizing marijuana. All right, well, we can use the central limit theorem. We could say that P hat is approximately normal, and its mean is 0.5. Its standard deviation is a square root of PQ over N, so the square root of 0.5 times 0.5 over 1,636. I popped that in my calculator, and I got that it's approximately normal with mean 0.5, and the standard deviation I got was 0.0158. Note, by the way, that P times N, or half of 1636, is a whole lot bigger than 5. Right? It's 818. And Q times N is the same thing, much bigger than 5. So that means I can actually say that we have a normal distribution for the sampling distribution. We can do all this information. So here's a picture. Notice that we have a normal distribution. The mean is 0.5. And we want the probability that P hat is greater than 0.67. So over here to the very far right, that's what we want the area of. So I put a question mark for that area because that's what we want. And now to find that, let's go to our calculator. So here's the calculator again. We want the low now to be 0.67. We want the high to be a bunch of 9s all the way to the right. The mean was 0.5, and the standard deviation was 0.0158. We want the probability, so I leave that blank, and I hit calculate. Notice it gives me 0, because it is such a small number. It's not truly 0, but it's probably like over 100 decimals before you get to 0. So it means that this can't happen. If you truly did a random sample and the mean was 50%, you're not going to get 67% of the people to respond that they agree with legalizing marijuana. So let's go back to the question and analyze it. All right, so what we found out was that the probability that p hat being greater than 0.67 or at least as big as 0.67 was basically 0, was so close to 0 it's unimaginable. What you typically do, and we're going to learn about this in a couple weeks or in the next few chapters, is you say, well, if it's so unimaginable, and we made that assumption that 50% or lower support passing marijuana as legalized marijuana, then this must be wrong. So what we can really say is that this can't be right. We really do have the majority of all Americans are in favor of legalizing marijuana. Now, again, you might be watching this 3 years from when I'm talking, and it may have already happened. But these are the kind of things that people have to look at when they're deciding to vote yes or no on something when it comes to a politician, is they should look at the public and say, well, if they know the public is in favor of something, then maybe this ought to happen. So this is pretty much everything I had to say about the central limit theorem. We talked about the central limit theorem for means. We talked about the central limit theorem for sums. We talked about the central limit theorem for proportions. And hopefully you'll understand now how to check to make sure that you can use the normal distribution if you have a large enough sample size, or if you're talking about means and the original distribution was approximately normal. And then you can find the sampling distribution's mean and the sampling distribution's standard deviation for its population. And then we can compute probabilities or percentiles using the central limit theorem. If you have any questions, let me know. You can ask me, or if you have a different instructor, make sure you ask your different instructor, and we'll be happy to help out. So thank you for watching this video.